When you spin a wooden top, it steadily slows down in a single fluid motion until it eventually tips over. But if we zoom in to the world of atoms, that smooth motion vanishes. At the smallest scales, particles follow rigid, stepped rules rather than sliding smoothly from one speed to the next. This can make subatomic behavior look like a flurry of random accidents. However, every tiny step a particle takes is actually directed by a hidden choreography that keeps the universe in balance. The secret to this choreography is symmetry, the simple requirement that the laws of nature must stay consistent, no matter where you are or when you look. Think about how the rules of physics don't change just because you move to a different spot. This sameness across space means there is no invisible force pushing or pulling you just for being in a new location. Because nothing is nudging you, you keep your current motion. Physicists call this the conservation of momentum. The same logic applies if you turn around. Because the laws of nature don't care which direction you face, there is no twist built into the universe. Without that twist, a spinning object will keep its spin exactly as it is. This is why angular momentum, the persistence of a spin, is so reliable. We also see this consistency over time. The rules of physics today are the same as they were yesterday. This prevents the universe from randomly gaining or losing strength, ensuring that energy is always conserved. When an electron obeys all three of these strict rules at once, it develops a permanent internal wobble that we call spin. Spin is a permanent internal characteristic of an electron, much like the color of your eyes or the weight of your body. It is a part of what the particle is, rather than something the particle does. These arrows show the two fixed directions an electron's spin takes, up or down. In our world, a 360-degree turn returns an object to its start. But an electron's spin must rotate 2 full circles, 720 degrees, to return to its original state. This mathematical requirement is our first clue that subatomic particles exist in a reality with much stricter geometric rules than the one we see. When placed in a magnetic field, a spin acts like a compass needle, pointing north while already spinning, creating a wobble called precession. Hitting that wobble with a precisely timed radio wave forces it to flip. This is resonance, changing the particle's state. This early MRI machine was built to harness those tiny flips. Your body is filled with hydrogen atoms, each with its own spin. The machine uses a massive magnet to make them wobble, then uses radio waves to flip them all at once. By listening to the energy released when those billions of spins flip back, the machine can map the inside of your body with incredible detail. We often imagine electrons as tiny balls, orbiting a center like planets. But in reality, an electron doesn't occupy a single point in space. Instead, the electron exists as a cloud of probability, representing every place it might be at any moment. Because of symmetry rules, these clouds are forced into specific shapes. They form perfect spheres or symmetrical dumbbells, but are never random or messy. These clouds also have a keep-out rule. They refuse to overlap with one another. Because these specific geometric shapes push against each other and stay separate, they create the boundaries that make the objects you touch feel solid. Mapping these invisible clouds and spins required a new kind of math. In the 1920s, 2 physicists proposed 2 different ways to read the quantum rulebook. Erwin Schrödinger developed wave mechanics. He focused on the probability cloud itself, showing how it ripples and changes over time like a wave. Werner Heisenberg took the opposite approach with matrix mechanics. He kept the cloud's shape fixed and focused on how the particle's properties, like its spin, changed as time passed. Even though their languages were different, their results were identical. They were simply looking at the same hidden choreography from 2 different angles. This chalkboard shows how those equations map out the exact energy levels inside an atom. Each line represents a specific, reliable step that every atom of that type will always follow. While an individual electron's position is uncertain, the rules governing it are incredibly stable. Quantum mechanics clearly shows us that even the smallest parts of our world follow a consistent geometric logic. Behind the apparent randomness of our lives lies a choreography of symmetry. It is the silent framework that makes everything possible, from the life-saving pulse of an MRI to the atoms that make us who we are.